Hi, good morning all. This is Dr. Manjunath Chennapgod from Anveshana Academy, Bangalore, India. Dear students, in the previous class we discussed about Otto cycles and we started some numericals on Otto cycles. Dear students, around 3 to 4 numericals we solved on Otto cycle. So today I am going to solve some more numericals on Otto cycle. Okay, so numerical on Otto cycle, dear student. Okay, so first I will try to read the problem now. Now I will read the problem. Okay, in a constant volume Otto cycle, the pressure at the end of compression is 15 times that at the start. Okay, comma, the temperature of air at the beginning of compression is 38 degrees Celsius and maximum temperature attained in the cycle is 1950 degree Celsius. Determine first one, compression ratio, thermal efficiency of the cycle, work done. Okay, so and he has given some data. Take gamma for air is equal to 1.4, that is specific heat ratio he has given, that is 1.4. Dear students, you can read the problem. You can understand the given problem is related to Otto cycles. Directly he mentioned here Otto cycles. Then what you have to do? You have to draw the Otto cycle PV diagram and TS diagram, and you have to list out the given data. Then you have to list out the important formula which are related to particular problem. Then you can solve this problem step by step. These students, as I told, solving problem is simple, but understanding problem thoroughly is very important here now. So we will solve this numerical step by step. Okay, so now what actually is telling now? He's telling there is an Otto cycle. So you can take it an Otto cycle, or you can call it as there is a petrol engine. It works. Okay, fine. And compression ratio he has given. The first given he has given some data. The compression ratio is 15. Sorry, pressure at the end of compression is 15 times that at the start. That means what? You can, dear students, you can call it as a 0.1, you can call it as a 0.2. So when the air fuel mixture gets compressed, right, then what happens? Pressure is going to increase to P2 from P1. So what actually is telling now, when air gets compressed, right, so that is something about what? P2, the pressure of the air when it is compressed is P2, that P2 is 15 times greater than P1. So that means what? It's initially, there is a example at BDC, at atmospheric pressure, the P1 will be generally 1 bar. If it is compressed, right, it is 15 times means what? 15 into 1, it will be around 15 bar. But he is telling, we don't know exactly the value of P1, but he is telling that P2 is greater than P1 of 15 times. That means what? What I can write now? So therefore P2 by P1 is equal to 15 he has given. That means what? Pressure ratio he has given in the problem now. So like this we have to note down one thing. Initially the temperature at BDC, when the temperature of the air is 38 degrees Celsius, when it is compressed, right, then when it is compressed, when we are going to add the heat to the air fuel mixture, right, then the temperature is going to change. That is nothing but what? Maximum temperature. Or else he is telling now, beginning of the compressor is 38 degrees Celsius and maximum temperature is attained in the cycle is 1950 degrees Celsius. Maximum temperature will be what? That is T3 is telling 1950 degrees Celsius. This data he has given now. With the help of this data, what you have to do? You have to calculate the compression ratio, thermal efficiency of the cycle, and work done. How to do this? That we can see here now, dear students now. Okay, so initially, so starting point is BDC, that is P1. He has given P1 and T1. Then he is telling that P2. P2 is something but what? It is a 15 times of what? P1. So therefore P2 is also is given. The next, when we is going to add heat, right, the cycle is going to attain maximum temperature at point 3 the maximum temperature is T3, that also he has given, that is 1950 degree Celsius. Okay, fine. Now this data he has given. Now you can see now, dear students, that is what I have shown. It is a PV diagram, but temperature you can get it from the TS diagram now. So here now at point 3, at maximum point, what we are getting? We are getting double to 23. That means what? He is converted, that T3 is equal to, is converted into 1950 degree Celsius. He has given, he converted into Kelvin by adding 270 223. Now this is what? Kelvin. This must maximum temperature he has given. Now this is a given data. With help of this data, what you have to do? This engine is working, right? How much compression rate is going to have? Then what is the thermal efficiency and what is the work done? We need to calculate. So step by step we will analyze the problem first and we will solve it in detail. That you can see here now, dear students. What is the first step now? We'll understand now. Compression ratio is asking to calculate the compression ratio. Compression ratio is nothing but what? As I told, dear students, assume that this is a point 1, this is a point 2. When it is at point 1, right, it is having the gas itself. You can see here now, the gas, whatever it is filled, right, it is having in a volume that is nothing but what? V1. When it is compressed, right, so when it is, just a minute, when it is at point 1, assume that piston, what actually this piston, we can say, when the piston is at point 1, it is having in a volume, that volume I will mark it as a V1. When the air fuel mixture is gets compressed, assume that if the piston reaches TDC, that means what? It attains point 2, then volume is going to become less. That means what? The air fuel mixture is gets compressed. That compressed volume is nothing but what? V2. The volume of the gas at point 1 is V1, volume of the air fuel mixture at point 2 is V2. Okay, fine. What is compression ratio now? We already know compression ratio is nothing but what? V1 by V2. Volume of air fuel mixture at point 1 to volume of air fuel mixture at point 2. That is nothing but what? Compression ratio. That I have already taken it out. Suddenly if it is compressed, right? That is nothing what? That is nothing but what? Isentropic increase in pressure and temperature. Once the air fuel mixture gets compressed, right, the volume changes to V1 to V2. Temperature also changed from temperature. I will mark it here, just a minute. Temperature also changed from T1 to T2. Okay, that he is telling now. Okay, fine. Next, if it's so, if you know the value working process of this piston cylinder, piston moving from point 1 to point 2, the volume is going to change. That volume change can be expressed in terms of compression ratio. That compression ratio is something about it is the ratio of volume of the air fuel mixture when piston is at BDC to volume of mixture air fuel mixture at point 2. That is nothing but compression ratio. Okay, fine. Next, if it's so, then you have to calculate thermal efficiency. Thermal efficiency means what, dear students? You are going to supply certain amount of heat, right? You are going to supply certain amount of heat, then it is going to do some amount of work actually. So how we are going to add heat? With the help of what? With the help of what? Spark plug here now. If it is a SI engine, spark plug. It is a Otto cycle, right? With the help of spark plug, you are going to add some certain amount of heat. That heat addition, I will take it here QS. Because of this amount of heat supplied, it is going to do some amount of work. So if it is doing some amount of work, with the help of now, what we can say now, this you can say heat supplied is input, heat supplied I will call here input, then work done is output. So generally we know, dear students, what is efficiency? Efficiency is equal to output to the input. What is input now here? What is output here now? Output is what? Work done by the engine. Input is what? Heat supplied. So if once you know the work done and heat supplied, you can calculate them efficiency. That efficiency is nothing but what? Thermal efficiency. Okay, to calculate this thermal efficiency, dear students, it required some data. What is work done now? I told work done, right? What is work done again? Work done, we have an equation QS minus QR. Okay, to calculate, sorry, now I will take it, you know. Okay, so this is nothing but what? Work done is equal to what? QS minus QR. What is QS? We know already that also. QS is equal to M into, it's a constant volume process, that is nothing but what? T3 minus T2. So dear students, to calculate the work done, I required QS. To calculate QS, you can see here now, M is constant, that is 1 kg per kg we are calculating. CV is the specific heat ratio at constant volume, specific heat at constant volume, that also we can get it, per air it is constant. But to calculate this heat supplied, I should know the value of what, T3 and T2. Then how to calculate that T2? That is our next step. We need to calculate T2 and T3 also. Once it done, right, once you calculate the T2 and T3, what I can do, I can easily calculate the heat added. That heat added is nothing but what, QS is equal to M into CV into T3 minus T2. Once it done, right, once you calculated heat added, once you calculated the heat rejected, then MCV into what, T4 minus T1. Once you know the value of QS and QR, what we can do, we can calculate the work done. So this is what, how to solve the problem, dear students. Okay, fine. Now 1 minute. Fine. Okay, so when it is point at 1, you can call it as a point at 2. Point at 1, it is having P1 and T1. When it is gas is compressed, right, when the piston moved from, when the piston, this piston is moved from this point to this point, that is 2, then what happens, it is going to compress, then pressure is going to change, volume is going to change, and also temperature also going to change. That I will represent is here, that I will represent here as a P2, V2 and T2. That's fine. Okay, V2, V2 and fine. Then when it is 2 to 3, right, what I'm doing, I'm going to supply certain amount of heat, then we're going to get a maximum pressure and maximum temperature, that is nothing but what, P3 and T3. Because of this, what happens, expansion will take place, adiabatic expansion will take place. If the expansion takes place, right, then what happens now, so we are going to get a point 4, that is nothing but what, temperature as T4 and pressure is P4 and volume is V4. These are the things now. But in this, dear students, you can see you are going to supply heat at constant volume. That means what, when V2 is equal to V3, then heat is going to reject at V1 is equal to V4 at constant volume heat rejection. So what you have to do, dear students, now to calculate work done, what you required, temperatures is required. How it is required, to work done, right, Q work done already I told you, right, that is what, QS minus QR. So what is QS? QS is equal to M into CV into T3 minus T2 minus QR is equal to what, M into CV into T4 minus T1. Hence, to calculate work done, we require temperature. To calculate work done, we require heat supplied as well as heat rejection. With the help of that, what I can do, I can calculate the work done. This is what, Otto cycle analysis. Then he is asking to calculate the compression ratio. To calculate the compression ratio, we require volume ratio. What is that volume ratio? V1 by V2. That volume ratio is required. Then once you know the work done, once you know the heat supplied, then what I can do, I can calculate the efficiency. That efficiency is nothing but it's a ratio of work done to the heat supplied. This is what the problem analysis. Now I have done the analysis of the problems. Now understood what he has given, what we need to find. Okay, now I will solve this problem step by step here now. So what is first step now? You have to list out the given data. What is T1? 38 degrees Celsius he has given. I will convert it into Kelvin by adding 273. Hence 311 K is the initial temperature, that is T1. Then he has given maximum temperature, that is T3. 1950 degrees Celsius he has given. Convert it into Kelvin by adding 273. So then 2223 Kelvin is the maximum temperature, that is T3 given. So now first finding is what, compression ratio. He is asking to calculate the compression ratio, that you can see here, dear students, in the problem. Okay, what actually is asking, is asking to calculate the first one, compression ratio. Next one, thermal efficiency. Okay, so now first, what is that, compression ratio is asking now. So to calculate the compression ratio, we are having an equation, V1 V2 to the power of gamma is equal to P2 by P1, pressure ratio. If it's so, but as I already told you, he has given P2 is 15 times greater than P1. That means what, P2 by P1 is equal to what I can say, 15. The same thing I have written it here now, P2 by P1 is equal to 15. It is given in the problem itself now. Now what is V1 by V2? Now I know the value of P2, that I will put it here 15. I will put it here 15. But V1 by V2 is nothing but what? V1 by V2, that also I told you, V1 by V2 is the compression rate, that is what, small r. So small r to the power of gamma is equal to 15. Now what is the gamma value? Gamma value is also nothing but what? 1.4. How you got this 1.4? That gamma is nothing but what? Specific heat of air at constant pressure to the constant volume. So you will get 1.4. Now R is equal to V1 by V2. I will put it R here, is equal to the power of what, 1.4 is equal to 15. So now you can see at the left and right side only unknown is what, R actually. I will take R here now. So therefore what happens, 15 to the power of 1 divided by 1.4. Do simplification, you are going to get the value of R as 6.9. This is nothing but what, compression ratio. Okay, the first finding is done. Now I will move towards next finding. What is next finding? Is asking to calculate thermal efficiency. To calculate the thermal efficiency, we derived an equation for Otto cycle. What is that equation? That we can see, thermal efficiency for an Otto cycle is equal to 1 minus 1 divided by R to the power of what, gamma minus 1. Dear students, you can see here now, what is R? That you already calculated, that is 6.9. Then gamma he has given in the problem itself. Then what we can do, you have to substitute all values in this equation, then you will get the thermal efficiency. To simplification, you are going to get 0.538 multiply with 100, you are going to get 53.8%. 53.8% is what? 53.8% is the thermal efficiency of the Otto cycle. Okay, fine. Next, third finding. What is third find? I need to calculate the work done. Okay, so how to calculate the work done? To calculate the work done, as I told you students, work done is equal to QS minus QR, right? So how to calculate QR? So QS and QR, as I told, QS is equal to M into CV into T3 minus T2. Similarly, to calculate QR, I require T4 and T1. So I mean, if I want to calculate the work done, I should know the value of T3, T2, T1, T4. For that purpose, with the help of adiabatic compression process and adiabatic expansion process, what I will do, I will try to calculate the value of T1 and T2. Now, what is the condition? So we know the equation. To calculate the temperature variation with respect to volume, we have an equation, that is T2 by T1 is equal to V1 by V2 to the power of what? Gamma minus 1. So what is V1? That is R to the power of gamma minus 1 is equal to, what is R value? 6.9. I will put gamma is equal to 1.4 minus 1. So therefore T2 by T1 is equal to 6.9 to the power of what? 0.4. So therefore T2 by T1 is equal to, you are going to get 2.16. Okay, so therefore T2 is equal to, what we can do now, this T1 you can going to multiply with the 2.16. So therefore T2 is equal to T1 into 2.16. Then what is T1? T1 he has already given in the problem. So add it now, because 38 degrees Celsius is given, you converted into Kelvin. That means what? 311 into 2.16. That means what? 671.7 Kelvin. You can minus 273, you will get 398.7 degree Celsius. Either you can express temperature in terms of final answer Kelvin or degree Celsius. But when you are going to simplify it, please try to put answer in terms of Kelvin to maintain the consistency in the unit. That's fine. Now I understood T2. T2 you can take it as 671 or 398 degrees Celsius. Fine. Now where you done? You have taken it in the compression process. Now I will go to the adiabatic process now. With the help of, so just a minute. With the help of 1 to 2 compression process, I have calculated the T2 value. Similarly, to calculate T4, what I will do, I will go with adiabatic expansion process. What is that condition? What is the equation? That is T3 by T4 is equal to V4 by V3 to the power of gamma minus 1. Whereas V4 by V3 is nothing but what? Expansion ratio. That we can call it expansion ratio is equal to what? Just a minute. Okay, so RC is equal to expansion ratio is equal to compression ratio is equal to expansion ratio. Hence, this is equal to R. That is nothing but 6.9. So therefore, what I can do, T3 by T4 is equal to V4 by V3 is nothing but compression ratio or expansion ratio. That is R. You can make it as a R to the power of what? Gamma minus 1. So what is R? 6.9. That you can substitute. 1.4 minus 1, it becomes 0.4. Then do simplification, we are going to get 2.16. So therefore what we can do, so you got it, right? You got it here now. So T3 by T4 is equal to 2.16. You got it. Now if you want to calculate T4, you can take it T4 outside, then T3 divided by 2.16. So therefore T4 is equal to T3 by 2.16. Do simplification, we are going to get 1029 Kelvin or 756 degree Celsius. This is nothing but what? T4. Okay, this is nothing but what? T4. Now you have calculated T2 and T4. Okay, to calculate the work done, I have calculated T2 and T4, but two more are required, right? T1 is given, okay, T1 given, T2 you have calculated, and you calculated T4, but you don't know the value of T3, right? Then T3 also you need to calculate. Okay, I will calculate that also. How to calculate the T3? Because we know what is that condition. Qs is equal to heat supplied mcv, we know the equation, T3 minus T2. So dear students, what about Qs is given or not? But okay, T3 is it required to calculate? No. But T3 in the problem you can go back and see. T3 is already given, that is double two one three something, right? 223 key, 3 Kelvin he has given. So therefore, you know T1, T3, everything you know here now. Then calculate the work done. To calculate the work done, what you require? Qs and Qr. So what is Qs? I will calculate here now. So therefore, heat supplied is equal to M into Cv. M you can take equal to per kg you are calculating. M is constant 1 kg. You can neglect Cv into T3 minus T2. What is the Cv? Specific heat at constant volume for air is 0.717. That I will you multiplied here. T3 is this much, T2 is this much. Do simplification, you are going to get 3112.3 kilojoules per kg or for air actually. Okay, now you calculated the work, the heat supplied. So that is nothing but what? Qs you have calculated. Similarly, what you need to do? You need to calculate the Qr also. How to calculate that Qr? That you can see here now. So what is heat rejection? To calculate the heat rejection, we are having equation again. What is that? M into Cv into T4 minus T1. Because again what I told, M is equal to 1 kg. That is a constant, you can neglect. Okay, so therefore Cv is equal to 0.17, T4 you already calculated 1029 minus 31, that Kelvin is getting answer because kilojoules per kg Kelvin something he want to maintain. So you do simplification, you will get the Qr value. Once you know the value of Qs and Qr, what you can do? You can calculate the work done. As I told, work done is nothing but what? Qs minus Qr. What is Qs? We already calculated, that is how much? 3112.3 minus Qr is nothing but what? 514.8. Do simplification, you are going to get 597.5 kilojoules, or 1 joules is nothing but what? 1 joule is equal to 1 Newton meter. So therefore, what I can write now? Kilojoules is the rate. What I can write now? Kilo Newton meter. So kilo Newton. If you want to remove this kilo also, multiply with what? 1000. So then what you can get? 59,000. Sorry, 5,97,500 Newton meter. Or else you can divide it by 1000. So then what you will get now? 59.75 something kilo Newton meter is nothing but what? Work done by the Otto cycle. This is how to solve the problem, dear students. This is what the final answer, what we are going to get. Okay, this is the final answer, dear students. Hope you understood this problem. If you have any doubts, you can comment and you can contact me. Dear students, please subscribe my channel, like and do comment and support me. Thank you.